I should pull my notes.
Just to confirm, you're planning on participating in the fall commencement, right?
Yeah, I've got one more semester to finish my comp sci minor.
Okay, great.
Ready when you guys are.
Let's do it.
Okay,
You want to be on that side? That's
Yeah.
fine, but I'll just readjust the camera then to include you.
Okay, so I'm Thomas, and I'm going to be presenting the research that I did for Professor Sean over the last year on investigating the viability of dark matter detection through wave propagation on a wire and displacement sensing. So just as an introduction, dark matter is non-luminous matter, which as far as we can tell, only interacts with standard particles through gravitation. And it's been proposed since as early as the late 1800s by astronomers who were doing calculations on the amount of mass they expected versus the amount of stars that they were actually seeing. But it wasn't until later towards the 1980s where it became to be an accepted question within particle physics due to evidence such as the galactic rotation curve, which is that we can observe that even as you get to great distances from the galactic center, the galactic orbital speeds of the observable bodies remains relatively constant. And so that implies that you have some kind of non-observable matter, which has a distribution which goes like, I think it's 1/r². So that way when you do the integral, the velocity stays relatively constant. And so the proposed explanation is that you have a kind of dark matter halo throughout the galaxy, which keeps the orbital velocities constant. And so, wrong computer. So there's been an ongoing search for dark matter, and in the 2023 P3 report, it was considered one of the kind of leading questions in particle physics, and they proposed funding for a diverse portfolio of experiments, and that's so among that you kind of have a lot of proposals for possible methods of detection. One proposed method is the wind chime project, which proposes using a kind of matrix of displacement sensors to be able to map an interaction with a massive particle. Essentially, even though the individual displacement is very small for each sensor, by looking at the displacement across all of the sensors, you should be able to kind of reconstruct the particle that they interact with. And so the research that Professor Sean asked me to look into was the possibility of using a wire as the mechanism of detection. And the reason that we thought this might be advantageous is that you have a lot more response to the sensitive areas of the detection, because rather than having discrete points, you have a continuous wire. And also because it should be more mechanically simple and cheaper, because you would only need a couple displacement sensors at the end of the wire rather than just a whole matrix of them. So the way that it would work is that
I can ask a
Oh,
question.
sure, I think so.
So the material is the same, the only difference is
you're proposing to use in the wire.
So-
Correct, or-
I don't think the material is the same because with the wind chime project, they're proposing like a matrix of displacement sensors. Whereas this is just gonna be a normal wire, and then you'd have a displacement sensor at the end of the wire, with the idea being that the interaction from this, a particle passing by will give an impulse to the wire, and then that impulse will create displacement that then propagates through the wire, following the wave equation.
I see.
And so in order for that to happen, you need the passing particle to have a pretty significant speed, because you don't want the wire to move at all while it's interacting with the passing particle. And so it requires that at the very least, the particle's speed is much greater than the speed of wave propagation on the wire. And so that impulse would be applied to each component of the wire and give them an initial momentum. And then that momentum would turn into a displacement that then propagates across the wire. And by measuring it at the end of the wire with a displacement sensor, we could reconstruct some of the particle's properties. And so the first thing that I did was kind of create a coordinate system, and the simplest one is this, where the wire lies on the z-axis. The particle track is on a plane parallel to the YZ plane, with the angle theta determining how parallel to the z-axis it is, and this distance b being the minimum distance between the wire and the particle. And so this is another reason that we want the particle to be moving with sufficient velocity, is so that we can approximate the particle's track that it moves along as a straight line within the frame of the wire. And so this vector r just tells is the vector between any point on the wire z and any point on the particle track determined by the time and the velocity of the particle. And so then by taking Newton's law of gravity, which is just gmm over r squared, and integrating with across all time, we can get the impulses that will be applied to the wire. And in this case, I replaced gmm with just a constant c. And so some things to note on the impulse is that the x component looks essentially like a Lorentzian, and this is because the x component of our vector between the particle and the at any point on the wire is essentially constant. So what determines the magnitude of its attraction to the particle is just how close on that point on the wire is to the point of closest approach between the wire and the particle. For
Thomas,
the
I have a question.
yeah.
I was studying your diagrams, and the point of closest approach of the particle to the wire, is that assumed to happen at z equals 0? Or can that
So
happen anywhere along the wire?
for all of my calculations, it's at z equals 0, but it should be able to be anywhere on the wire. And if you're able to measure both the longitudinal displacement and the transverse displacement, you would be able to determine where that point was based off the difference in time between the longitudinal wave arriving and the transverse wave arriving at the same point.
Okay, thank you.
So for the y and z components, they're very similar. The only difference is a factor of cosine theta rather than sine theta, which just changes where the maximum points and where the zeros are based off of theta. But they essentially act like a kind of pinching impulse. If you were to think of the wire and a particle passing by here, all of the components of the wire below where the particle passes are going to be pulled upwards, while all of the parts of the wire above are going to be pulled downwards. And also the other big thing is that because they have a factor of z in the numerator, they don't go to zero as fast as the x component along the y-axis. And so the next thing that I did was I used the method of finite differences to simulate what how the momentum would propagate into displacement as time passed over the wire, so that we could kind of get an idea of what solutions we might be looking for. Mouse. Okay, well, this did not export correctly.
Oh, where is it?
Yeah. Um, I can,
Why don't you describe what the movie was going to show? I think that's
yeah,
okay.
So essentially you start with a very large impulse. It's about twice this, it goes up to about here, and there's no displacement. And then half of the impulse will move in each direction. So it drops down from the maximum kind of impulse down to half of that size, and then they each move in each direction. So you get a velocity, a pulse of velocity in each direction, propagating in each direction, and then the displacement gets essentially along at this, after the velocity moves past a point, that point's displaced up to a kind of new resting point, and it will just stay there as long as momentum's conserved. So until the wave is reflected and comes back with the opposite amplitude, the wire would just stay up here, or some other thing that didn't conserve momentum.
It's a shame if we can't see the animation. Do you
Yeah.
have an easy way to pull it up? Is it on Google Drive or something?
It is on Google Drive, so I could probably open it up on Firefox if I took a
Yeah.
minute to
I
log
think
in.
it's worth seeing because
Make it easier.
it's what
Make it easier.
yeah, because it was an interesting
Sure.
thing that we
I would like to see, yeah.
learned how to think about this.
While you're doing that, can you remind me, how long of a wire are we likely to be talking about?
So the one that I did all of my calculations with was 2 meters long.
Okay,
Um,
2 meters under tension, if I remember correctly.
yes, sir.
Yep.
Or possible.
The problem with password saving apps.
I have the same issue.
Okay.
Thanks.
Yeah, so this is the X component.
Can you make that larger part of the screen?
Yes.
Thank
So,
you.
So as you can see, you start off with this kind of very large initial velocity, and then it splits into two pulses of equal magnitude, both about half the initial velocity, moving in opposite directions. And then you end up with this displacement where the wire kind of just gets moved to a new resting point.
This is something I did not really expect. Maybe if I puzzled over it, I could have thought of it, but I didn't. You know, that this is what happens for for locally impulsed wires that just move sideways.
And essentially what we figured is that it's gonna remain in this new position and as long as momentum's conserved. So if when this wave were to reflect off of a fixed end and come back with the opposite amplitude, it would then return the wire to its initial position. And so then for the Z component, you get the same thing where you have kind of an initial velocity. In this case, it's rather than being just a attraction, it's more of like a pinch. And so then it does the same thing where it splits into two kind of equally sized, same shape pulses moving in opposite directions. Though in this case, because of that, the fact that the impulse doesn't go to zero along the wire as quickly, you end up with it getting them being constructive with constructive interference that makes them kind of slightly skewed in opposite directions. And then for your displacement, you get this kind of like peak of displacement and then it goes back, but it doesn't quite return. But as you can see, again, because of that factor of not going back to zero, you get some displacement kind of leading to it. And then I think yeah. And so the next thing that I did.
Wait, I just want to understand. Can you put that picture back up?
Sure.
All right, so on the left at minus 0.06, let's say.
Right.
There's a displacement in the Z direction of positive amount.
Yes.
And then on the right, there's a displacement in the other direction. So the string has been stretched or compressed. I think I know. I just want to make sure. It's stretched, right?
I believe it's being stretched, yeah.
Okay.
And if you think of it, if there was an initial pinch kind of, so in this case, there was an initial pinch in the center
Yeah.
of the wire, but then it splits into two pinches which move in opposite directions. So if it's being pinched around this point and around this point, then where it's not being pinched, it's going to be kind of stretched in that direction.
Yeah.
But at all negative Z's, it's got a positive displacement. So I think there's still an overall pinch in a sense.
Right, yeah.
There are two localized concentrations of pinch, but there's also kind of
Because essentially like all the wire down here is being kind of like by it's being pinched here, so it's displacing a little bit that way to kind of.
Oh, it's stretching the rest of the wire.
Yeah, that's my.
Yes, okay, right. I see what you mean by that. Yeah, it's stretching the wire beyond. Yeah, it's pulling wire in.
Yeah.
Yeah.
Okay, so then the next thing that I did.
So you can hit
Yeah,
from current slide if you want.
I'm just gonna end up
Okay,
showing another
sure.
animation, so
Okay,
I figure
sure.
I might as well not.
Yeah.
So the next thing I did was kind of work to try and create to be able to find closed form solutions to be able to recreate that same thing. And the idea being that you'd have kind of two traveling wave solutions that are destructively interfering at the initial time so that you have no displacement. And then as time evolves, they kind of stop destructively interfering. And I have some animations for those too, if I can show you. I wish this one automatically play. Okay, so once again, this green one is the displacement. You can see it's not displaced at all. And then this is our initial velocity. And then it does pretty much the same thing where it splits into two pulses moving in opposite directions. And then you get destructive interference where the pulses haven't yet reached, and then constructive interference where they've already passed. So that's for the X component, and then for the Z, the same thing we were just talking about. So the way that I found those solutions was I took the initial conditions for our wire, which are that it's not displaced and that it has this initial momentum from its interaction with from the impulse that the particle gave it. And then I split the magnitude of the momentum into two, and then replaced Z with Z plus or minus WT for so that we have a left and a right traveling wave, and integrated with respect to time. And these are the equations for the displacement that I got. And I'm just going to point out the kind of what I think are the most important parts of these equations, which are that, first of all, the overall magnitude of the equations depends just on GM over V, and then the 1 over the wave speed. And so that means that kind of the only variable that we can control in terms of maximizing the displacement from any particle is the wave speed on the wire. And so that's going to depend for the longitudinal waves, which is the Z component of displacement. That's going to depend on the Young's modulus and the mass density of our wire. And then for the transverse waves, it depends on the tension that we apply to the wire and the linear mass density. And then the other thing to note is that the physical properties of the wire in its mass and its velocity only really affect the magnitude of the displacement. They don't really affect the shape. And so in terms of what particles could we detect with the setup I was looking at, it would be ideal if we could test our ability to reconstruct the particle properties with neutrons, since we're able to generate neutrons and we can bring them down to pretty low speeds. But unfortunately, in order to get displacement on the order of nanometers, which is kind of the limit of modern displacement technology, sensing technology, as far as I could tell, you need particle speeds lower than 10 to the negative 29 meters per second, which just is kind of ridiculous, and it violates our principle of having particle speed be much greater than the wave propagation speed. For dark matter, if we wanted displacement on the order of 2.4 nanometers, which is the resolution of the capacitive sensors that I was looking at, then for the transverse waves, you need mass on the order of 10 to the 8 kilograms. And for the longitudinal waves, you need mass on the order of 10 to the 10 kilograms. Something that was interesting about this is that even when increasing the minimum interaction distance, these values didn't change significantly, particularly the one for the X component. And when I graphed it, you kind of see that when you're below the scale of the length of their string, you don't really have that steep of an increase in the minimum mass required. And it's kind of, once you get further out, you get a much steeper slope. And so just what I was going back to what I was talking about earlier in terms of how the properties of the particle and its track affect what we're able to detect. The shape of the curve only really depends on the track's properties. So that's the minimum distance and then the angle of the track with respect to the wire. And as you can see for here, we have a neutron from a deuterium generator, which I think is like 2.4 mega electron volts. So that's a neutron moving at about 2.7 meters per second. Whereas if you were to put that through a moderator and bring it down to being like a thermal neutron, then it's moving at more like 2.2 kilometers per second. And you can see that the shape of the curve doesn't really change at all, but you do see that the magnitude changes directly with that move from from 10 to the 7 meters per second to 10 to the 3 meters per second. You can see that the magnitude goes from 1e negative 45 to 1e negative 41. And so that kind of to me shows that if you had a sensor which is able to plot, which is able to get several data points as the wire is displacing, you could fit the kind of shape of that displacement with respect to time to the expected functions and reconstruct the m/v ratio of the particle. And so one of the possible setups that we looked at was with a hanging wire being tensioned by a massive bob and then using capacitive sensors to detect the displacement of the wire. I chose capacitive sensors because they have good range and they're relatively cheap. And we need the tensioning bob in order to get a relatively constant tension on our wire, as that lets us assume that the wire has no displacement to begin with, and it lets us assume that we have traveling wave solutions. But unfortunately, it introduces complexity from the dynamics of the tensioning bob itself. It's essentially going to, for any wave that hits it, it's going to act like a fixed end and reflect that wave. But in doing so, it gains twice the momentum of the wave, which happens to be the initial momentum. And so the next thing that I did was kind of try and investigate how the bob would then move from that momentum. And so for the transverse waves, the momentum is going to be perpendicular to the wire axis. And so my thinking was that it would likely undergo simple pendulum movement because it should be very small displacements. And so by using by using the potential of moving the bob and the wire as the potential energy that is going to be going against with its initial momentum, I was able to determine kind of the maximum transverse displacement. And I actually found that to be several orders of magnitude greater than the expected displacement of the wire itself, which I found very surprising. Unfortunately, for the longitudinal waves, I did not find that. I found that its maximum displacement would be negligible. I went under the assumption that if you have a transverse wave, it's going to end up with a net upward momentum because of that pinching motion that we were talking about earlier. And so you'd end up with the tensioning bob either trying to compress the wire as if it's undergoing like a simple spring motion, or trying to lift the wire, in which case, rather than having a spring constant, spring potential here, you just have this potential again. But either way, I found negligible displacement. So unfortunately, if you have a tensioning bob, you would need something other than capacitive sensing to measure the longitudinal displacement of the wire. I think maybe you could possibly create a setup with a strain sensor, but I was not able to figure that out. So another thing that we considered was, what if you were to just have a hanging wire by itself with no tensioning bob, because that would give you several advantages in that you would be able to measure the vertical displacement of the wire, and it would minimize the tension on the wire, which based off of the kind of inverse relation between wave speed and displacement from our previous equations would increase the displacement we would see. Oh wait, this is the wrong slide. I got sidetracked onto something else. This is, so if you do use a tensioning bob like this, we thought that you would, because you want tension to be essentially constant, we chose a tension based off of the total weight of the wire. And what's unfortunate about that is that it removes the dependence on on linear mass density from your transverse wave speed, and you end up only kind of having a dependence on the total length of the wire, which means that your wire choice would no longer, your choice in material for wire would no longer affect how much displacement you would see. It would still affect the longitudinal waves, but as we said, if you have a tensioning bob there, we can't really detect the longitudinal waves anyways. Back to what I was talking about, which is removing the tensioning bob. So you then get a tension that varies with the wire length if you have the wire being only tensioned by its own weight. So at the top of the wire, it'd be tensioned by the entirety of the weight of the wire, and at the bottom, be under no tension. And we were thinking that this would mean that since your tension is varying slowly and continuously along the wire, that maybe you'd be able to find an adiabatic invariant in the system with units of momentum times displacement. And so tension times displacement divided by wave speed has those units. And that would imply that displacement squared is inversely proportional to tension over wave speed. And therefore, the displacement should be inversely proportional to the square root of linear mass density. But if we plug this tension into our equation for transverse wave speed, we don't see that dependence at all. And this is because this equation for wave speed assumes the dispersion relation of linear mass density times frequency squared equal to tension times wave number squared. And this is found by assuming that our solution is going to have the form of a function times kz minus omega t, where both k and omega are constant. However, if tension is varying, we cannot assume that k is constant. And so that means that if we wanted to be able to solve, to determine what kind of waves we'd see if we just had if we had varying tension, then we'll need to find new solutions and solve the wave equation to find a new dispersion relation, which would be much more complex. And we were not able to do that in the time that I had. Another possibility that we considered was using the same concept for charged particle detection. You just end up with different constants. In this case, the most important part of the change from Newton's gravity to Coulomb force is that you end up in your displacement equations having, or in your initial velocity, having a factor of dq over dm, which is the same as charge density over mass density. And so you need to consider the ratio of charge density and mass density when trying to maximize your displacement. And also, if you're using electrostatics, then unlike mass, because charge can be positive or negative, you'd have to expect both attractive and repulsive interactions. So for the charged particle, if you have, in the static case, the equation should be the same, except that you have to allow for both attraction and repulsion. And ultimately, the displacement would come down to how much charge you can gather on a wire. Whereas for the conducting case, we would expect a larger impulse because the charge density will distribute across the wire to maximize attraction with charge of the opposite with opposite charge kind of gathering on the ends of the wire. But because the charge density wouldn't be uniform across a conductor, it would not be the same family of solutions as we found for massive particles. So in conclusion, a massive particle moving with sufficient speed should provide an initial impulse to a wire, which would then displace and propagate down the wire. And by measuring this displacement, we should be able to reconstruct properties of the particle. And we would require for dark matter moving at galactic orbital speeds, which is kind of a lower bound on the speed for dark matter, we'd require masses on the order of 10 to the 8 kilograms or larger. And so some things that I think might be interesting to research further for the setup with a wire and a tensioning bob, I think investigating whether measuring the displacement of the wire or the bob yields better results is something that could be further investigated. Particularly, even though my initial analysis suggested that the bob has greater displacement than the wire, I'm a little suspicious of that because the bob has a much greater mass than every individual element of the wire. So I would have thought that it would have moved less. And also for that same setup, it would be worth investigating how you can detect longitudinal waves, because as we discussed earlier, the difference between when a longitudinal wave arrives and when a transverse wave arrives would be able to tell you where that point of closest approach between the particle and the wire were. And then finally, investigating the case for varying tension might give better results, but it would requires kind of a much more in-depth analysis of the wave equation and those with the tension varying. So I wanted to thank Professor Sean for giving me the opportunity to do this research, my friend Ruby Duncan for helping me proofread and edit my report, and then you guys for coming and listening to my presentation.
Terrific. I'm not in the room, so Peter, I have a question, but you can decide how to go.
No, why don't you go ahead? And you're not really visible to the others. Oh, you're still there. Yeah.
Yeah.
But go ahead.
Okay, so I was curious from what we know about dark matter and the amount that it would take to produce the rotation curves that motivate the search. How often will a particle of this mass approach the wire sufficiently closely? Is this going to be something that happens every few years, or is this something that'll be happening all the time and you'll have to integrate multiple passes? How's that going to work?
I'm not certain because I'm not super knowledgeable on dark matter, unfortunately. Based off of what I was researching and reading other people's kind of proposals for dark matter detection, I think it's something that you would not, from my understanding, it would not be a super frequent event. But I could be wrong on that.
Can you
And
think,
so if it, go ahead, whoever's there.
I was just gonna say, can you think of how you could estimate it?
I think when there was one of the other papers I was reading talked a bit about like in terms of trying to predict kind of like what, in terms of trying to predict the like what kinds of particles they would see. They were trying to like predict. They talked a bit about like looking at primordial black holes and stuff like that. But they were one of the things that they mentioned was the limiting factor was the fact that I think primordial black holes that are small enough that they would kind of like only be observable through a very precise detector would have likely already like burned themselves out but again, it's not like super my field of expertise. I think, yeah, unfortunately, I can't give you a more in-depth answer to that.
you want to
If-
follow up, Bill? Go, yeah, I interrupted you before. Go ahead.
No, please, it's easier.
Well, let's see here. From the rotation curves that are seen for the galaxy, you must be able to know how much, you infer how much mass is within a certain volume
Yeah.
of the galaxy. I don't know how this works out exactly,
think-
but
So my understanding from it's on, let me.
I just realized that the camera got turned off here. Sorry about that.
No, it's all good. I'm following.
So from what I read about, my understanding is that so as far as I read in terms of the galactic rotation curve, it was kind of just, I just kind of just wanted to get an understanding of where this kind of number for a minimum speed that you would expect dark matter to be moving at came from. And so that was kind of reading up to the point that, like, for something in a Keplerian orbit, you'd expect velocity to be proportional to 1 over the square root of radius from the galactic center. But they observe it as being relatively constant. And so the theory with the dark matter halo is that there's dark matter with a mass density which is proportional to 1/r squared, because then the kind of mass distribution of the universe would be proportional to r, and so then it kind of cancels with that 1/r factor when calculating the velocity of something in Keplerian orbit. So I think you could probably give so based off of that, I would guess that you could predict how much mass you would expect at each kind of radius at each kind of like shell of radius from the center of the galaxy. And so you would probably be based off of like how far our solar system is from the galactic center. You could probably then kind of get an idea of how much mass is it within that kind of spherical shell, and then from there kind of determine how much mass you would expect within the orbit, like to kind of be passing within the orbit of our solar system. I would not be able to say more than that, but I think probably you could, if you got someone who knew those numbers, that they could probably give you an answer on how frequently
Right.
to see.
Yeah, so I agree with that. You could do that calculation. And then there's one more thing though, that is that mass in a few massive particles or in many, 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 many very light particles? And so I guess in the latter case, you would not expect to see anything.
Yeah, so I do not actually know the answer to that question, but I would guess that the idea is that it's in many smaller particles, just because of the fact that I think when they have these observations of kind of galactic orbital velocities, it's from my understanding, it's pretty much everything that we have been able to observe the speed of is moving at like pretty much the same speed around the galactic center. And so I would think that if you want kind of everything, like that would mean that you kind of need a pretty continuous distribution of mass. Because I feel like if it was if it was concentrated in just kind of several very large particle, if it was just very large concentrations of mass, you'd end up with not, with kind of a more, like, with a less continuous, well, with less constant speeds, right?
Yeah,
Because you wouldn't
that's
have
good.
a-
You've just sketched out an observational limit on how big, how massive the dark matter particles could be. So, I mean, that, you know, by saying that that would affect the uniformity of this. So, so that's a good constraint at one end of the spectrum.
Another
Mhm.
question I had was, you've considered everything on a straight wire.
Mhm.
Is there anything that you see or that you calculated that leads you to think that setting things up like with the wire in a circle or in a helix, is there any advantage to any other shape? Or, you know, have you thought about that yet?
I haven't seriously thought about it. I would think that, so I think for a circle, I can't imagine that offering too much of a benefit, just because I think it would make it much harder to measure the displacement. A helix could potentially be interesting because then you kind of end up with a bit with more mass concentrated near that like sensitive area of the interaction. So I could potentially see getting more of a response from like a helical wire. I guess the main kind of limiting factor on having a more complex shape for your wire is the ability to create closed form solutions to the expected displacement, because you kind of need to have some kind of like closed form prediction for what your displacement's going to look like if you want to perform a fitting, which can let you kind of extract the properties of the particle, rather than just being able to say that, you know, there was something that caused displacement, and being able to say, well, based off of the shape of this displacement, then whatever caused this displacement must have had this ratio for mass over velocity.
Well, I want to challenge that slightly. Surely it's better if you have a closed form solution, but computing is cheap, and you could imagine templating out lots of predictions. And if there were some significant advantage to having a tightly coiled helix or some other shape, I think you could, I'll let you comment. I think you could, maybe you wouldn't have a closed form, but you could characterize the displacements pretty well with a campaign of kind of simulating different trajectories and so forth, couldn't you?
Yeah, I'd agree with that. I think if you had I think if you were able to find a kind of setup that, you know, that did kind of give you those optimized results, then through simulation, you can definitely kind of create a map of like expected displacements and use that to kind of match with any actual measurements you made. So yeah, I'd agree with that, that if you're able to find yeah.
So I guess when I was just kind of dreaming, I was thinking, you know, do I want a wire? Do I want a slinky? Do I want something else? And I haven't done the calculations, but I suppose you've told me what you would do to evaluate that, which is fine. That's good.
Yeah, I think essentially if you had a more complex shape, it would come down to calculating the impulse that a massive particle would apply to that.
Yeah,
And just kind of using some form of simulation to see how that impulse would propagate into displacement.
right.
Yeah, I think the idea of having a helix or something like that is interesting because one particle then could be applying an interesting pattern of impulse to the different parts, to the different loops of the slinky, and you essentially could create multiple pulses all from the same passing particle, and that would be a very distinctive signature to arrive at your sensor at the end of the wire, that end of the slinky in that case. And distinctiveness is good because if you're doing this in reality, you need to distinguish against noise and vibration of your apparatus. And if you've got some sort of distinctive pattern that a passing particle can produce, but vibrations of your apparatus don't do that,
Right.
that gives you a handle for using match filtering or something. So that's an interesting point.
And then I guess I should let, Man, do you have any questions? I don't want to dominate.
No, I think that's a good question. I also actually planning to ask a similar question, but something following your question about why I'm curious to see practically could a wire could the materials of the wire going to play a certain role in your
Yeah, so the main things that the wire material affects are so it affects that your initial impulse magnitude in that the more mass you have in the wire, the more attraction that it's gonna have between it and the particle. But that actually, from my understanding, because your initial velocity is impulse divided by the kind of mass of each segment of the wire, that kind of gets like canceled out from the initial velocity of the wire. So even though it kind of increases the impulse that you would see, it doesn't really affect the initial velocity. So the other place that it would play a role is in your wave speeds, because the Young's modulus and the mass density affects your longitudinal and transverse wave speed. So, and because of this, at least for the solution with a straight wire, you end up with an inverse relation between displacement and wave speed. You want something with kind of a low Young's modulus and then a heavier wire. And my understanding of that is that essentially by having the wave move, propagate slower along the wire, you spend more time with that velocity being, with that up, you spend more time with like kind of an upward velocity being applied to kind of a segment of wire. And so it gets displaced more before the momentum kind of moves past it. So from what we were, for this, the solutions that I found, the kind of material choice is mainly that you would want a heavier wire with a lower Young's modulus.
I see. So that is a guideline when you. That's good.
Yeah, I think for the calculations that I ended up doing to get these numbers, I used a copper beryllium wire, just because of it had from the materials that I was looking at, it had a pretty low Young's modulus while also having a pretty high mass density. But I didn't do like a super thorough search through wire materials.
Yeah, I'm sure that they probably have other material that can do better by following your suggestion. But that's good.
Yeah, I think there was when I was in the first semester, I actually looked at I was looking at accelerations, like rather than looking at displacement, I was looking at acceleration and force applied to the wire. I'm not entirely sure why. Especially because there's like, in the initial reading that I did, there were like 3 places where it said, you know, force detection and force detection is based almost entirely in displacement. And for some reason that just like didn't enter my head. So I didn't look at displacement until the second semester. But one of the interesting things that I came across was that they kind of created very, very precise capacitive force sensors through looking at the capacitance of you have like a kind of carbon nanotube filament, and then you look at how that gets displaced with a force.
I only had one other speculative question just to see how you think about these things. Instead of a wire or a slinky, what if you had, you know, you think about hanging your laundry out and you had a sheet of material hanging? Is there any reason you didn't start there? I mean, I would imagine you start with a wire because the calculations are first of a kind and you need to work it all out. But having thought about it, would there be any value in having a plane instead of a wire?
Yeah, it's been a while since I did those more complex wave solutions. I would think not, and the reason is that I think that your impulse, you'd have kind of, like I imagine that if you had a sheet, you'd get a very strong response along one kind of like strip of that sheet where where the particle is passing close by.
Yeah.
You'd get a pretty weak response in the rest of the sheet, and then you'd have that momentum. My guess is that momentum would kind of propagate and spread across the whole sheet. Whereas in a wire, because it can only move in 2 directions, it stays relatively concentrated. If you remember from these animations, you have this initial momentum that splits into just two momentum pulses moving in opposite directions. And so my guess is that if you have a sheet, you'd end up with the momentum being split into like a whole, rather than just 2 points moving in opposite directions, you'd end up with like a kind of maybe a radial pulse moving away from that kind of strip. And I think that you'd end up with my guess is that you'd end up with a lesser response to a particle of the same mass, just because that momentum's getting more spread out.
Good. That seems reasonable to me. I don't know how you guys feel in the room.
Well, my take on this was, I figure if you can build 1 wire detector, you can build 200 of them, and you can string them up in parallel and put them in the same vacuum chamber or whatever you're doing with them. So because you need to somehow get, I think it helps to get a large sensitive area. So doing a sheet is one way of doing that. But my thought on it was just an array of wires, and I tried so hard to figure out that if the detector could be called like the wire array for relativistic particles, so that you would have a catchy acronym for the name of this detector.
Yeah, warp. Yeah.
Warp, which is exactly what it is from a weaving point of view, right? It's the warp. Yeah, a bunch of parallel wires. So it would be just perfect. So why not build it?
Nice.
Is that what motivates all science? Just having good acronyms?
That's like day 2 of the inspiration process. Is okay. Now what can I call
It's
this?
good to understand.
All right, I have a kind of final question here. Okay, so you've done calculations here. You've estimated, what mass dark matter particles this could do and all that. On the one hand, you could look at these things and you could say it's hopeless, or is it hopeless? What is your take on whether it is or isn't hopeless? And if it is hopeless, is it or isn't it worth like publishing or advertising a study like this anyway?
So based off of my understanding of what we know about dark matter and the possible particles of dark matter out there, it doesn't seem hopeless to me, just because we don't really know what mass those particles would have.
Yeah, probably your upper limit that you were talking about earlier is way, way beyond the 10 to the 8, 10 to the 10 kilogram.
Yeah.
I mean, I know it is, but
Yeah, I think the
yeah.
upper limit is significantly larger than
yeah.
that.
Uh-huh.
I think the real question is, like, if you have something that gets to those larger masses, is it really gonna have only this small effect within the observable, like within what we can observe? Because it's kind of crazy to think of something with like, you know, something with 10 to the 8 kilograms of mass, just like moving through your lab and it only creating like a nanometer of displacement on the wire. Like, that's, to me, pretty crazy to think about. So I don't think it's necessarily hopeless. And also on top of that, you know, displacement sensing, I think, is pretty active field. In fact, there's been a couple of the internships I applied to at the Greenbelt NASA location are on coming up with more precise displacement sensors.
Mm-hmm.
And so, as you know, as the sensitivity of our equipment, you know, increases, it kind of just increases the range of masses that you'd be able to measure with something like this. So I don't think that it's kind of like hopeless, but I do think that there's kind of a lot more complexity that would be worth looking at in terms of the kind of real world expectations and complications of building one. You know, because like in my presentation, you know, there were still a ton of questions that we had about, you know, it's a little slow. You know, there were still a lot of questions about whether this is, you know, even the best option for it. So I think that it would be, you know, I think that it is not hopeless, but it would warrant more investigation in terms of what actually building it would look like and what kind of setup you'd actually want before you kind of really were to publish your results.
Okay,
I thought
that's fair. Good. Okay. I mean, yeah, I think of it as, you know, even if you think you can't currently build a detector that can do this, putting that information out there in the analysis might motivate somebody to come up with a way and say, okay, I can't build you a general displacement sensor that does this, but if you wanted a differential displacement sensor between two closely spaced wires, you know, now we're talking about a specific case where maybe we can do to picometer level or something, or, you know, an interferometric measurement. I wonder if you can take these wires and illuminate them with some laser field and be imaging the diffraction pattern some distance away. And I haven't worked through any of the numbers, but, you know, maybe there's, you know, the subtle shifts in diffraction pattern actually tells you about a very small displacement of the wires or something like that. I wouldn't be surprised if there's something.
that'd be really cool to look at.
Mm-hmm. Okay, but
Very good.
all right.
Thank you.
Thank you, Tommy. And thank you, Bill, and thank you, Min, for
See you guys.
being part of this. Yeah.
So anything we need to do, or we are done, or no discussion?
I think we don't have any like official forms for this, right? You just file this away for future use, I think, right, Bill?
That's I will send an email to Min and Peter. It just documents what transpired. And Thomas, congratulations. You've done a nice job here.
Thank you.
And I hope you'll keep in the field of physics. That's good.
Definitely,
I think he's gonna take a
too deep
video.
now.
Good. That's good.
Very
That's
good.
Yeah, see you, Bill.
Thank you, gentlemen.
Yeah, I mean, there was a
Hi, Bill.
couple things, there's an internship that I